Welcome back. We're going to be looking at another example. This is probably one of the more bizarre material balance example problems. This problem is, this is the drawing I came up with. Old Fred receives 120 eggs per minute. When they leave him, 30% of those are broken. They then go to the separator, which has large eggs and extra large eggs that are 70 eggs per minute. Of those, 25 are broken. We don't know how many whole are broken in the other streams. So this is technically two separate pieces of information. We're starting to get ready for doing multi-component systems, but I think that you'll see that this is not all that complicated. So I have my streams. I'm going to label these A, B, C, and D just for simplicity. And I have my material balance table I can create. I have whole eggs and I have broken eggs, which add up to the total. The total in stream A is 120, as is the total in stream B. The total in stream C, I don't know, I'll just call it C, and the total in stream D is 70 eggs per minute. Okay, so now then, how about whole and broken? Well, in the feed stream, I have 120 whole eggs, and I have 0 broken eggs. And here I have no idea. I have 30% of them are broken. And so let's call this, what do you want to call it? How about little a and little b? Okay. All right. So this is my material balance table. What about my degrees of freedom? Well, here, let's just talk about old Fred as a process, and let's talk about the separator as a process. So we'll do these two different ways. So my streams on old Fred, I have A in and B out. And my variables, I have little a and little b, so I have 2 variables. My material balances, I have 2 types, so my material balances I can do whole and broken. Sum of x's, well, I'm not using mass fractions, okay? So that's going to complicate things a little bit, but in this case, what I'll have is a plus b equals 120. This is going to be a sum of x equation. So I have 1 here. Process specs, I have 0. Degrees of freedom, I have -1. So in fact, this is, overspecified, this problem here. If I look at just the separator, okay, the separator, I have stream B coming in, C and D coming out. My variables, I have little a, little b, little x, little y, little z, and capital C. So I have 1, 2, 3, 4, 5, 6. Okay, I have 6 variables here. The material balances, I get 2. Sum of x's, I get 1, 2, 3. Process specs. Well, okay. I do actually have a process spec. I have not used that. I guess I had a process spec over here too. That would make that -2. And so 6 minus 6, I have 0. So this is a well-posed problem, is what I'm basically trying to say here. I have all of the things I need to do. So let's look at this, see if we can solve this problem. So let's just start over with a clean drawing and start writing down what these equations are. I'm going to use my process spec first. Process specs are typically nice to get out of the way. And it says 30% of the eggs are broken. So my number broken is little b, okay? And that is going to be 30% of the 120 eggs per minute. Okay, so 30% of 120. Wow, wish I could do math. Okay, so I have my number broken right there using my process spec. Okay, I also can use my sum of x equations. The one I could use any of these, but so a plus 36 equals 120, and therefore I could solve for a. And then I also have z plus 25 equals 70, and so I can solve for z. All right, so next I can do my material balances. And you could have done these in any order, just so I know that total 120 N equals C plus 70. So C is going to be, okay, and then I can solve for X and Y. I could do a whole egg balance, I guess. So 84 equals little x plus z, which we've determined to be 45, and so forth. So I can go through and write all of these equations and get all my answers. So let's go through and see, how do I answer the question? Is old Fred right or left-handed? Okay, well, let's think about what fraction of the eggs are broken. Okay, so in the large stream, the fraction broken is little x. Okay, I guess I didn't ever say what x was. Okay, so he broke 39 eggs per minute out of the 50 that he had. Oh, excuse me, that's whole. Excuse me. Okay, so he broke 11 out of 50, okay, which is 22% broken. What about the extra large? Well, he broke 25 out of 70, which is 36% broken. So now, in order to answer the question, I have to make an assumption. When you make an assumption, it is best to write that assumption explicitly into your work. So I am going to assume that he's a little clumsier with his offhand. In other words, you can be a little more delicate with your primary hand. Okay, so he's more delicate with his large hand and more clumsy with his extra large hand. Okay, this was the right hand. This was the left hand. Therefore, I say old Fred is right-handed. Now, clearly, if you made a different assumption, your logic may come to a different answer, but as long as you very clearly state your assumption, then no problems. Okay, so that concludes our introduction to material balances without reactions. I do want to make a couple of small points. So we've talked about using a basis. And so far, all I've done was I say that that's something you assume as a flow rate at the beginning. Why? Well, the reason we're using a basis is it allows me to fairly easily come in and change the problem statement. So earlier we had one where we had a certain flow rate. I don't remember exactly what it was that came in, and we had 0.5 grams per minute of water that left and 22.7 grams per minute of dried air. Okay, so now then what we do is we use this because this was my original basis. Now then we're going to increase the flow rate. I want to change the flow rate let's say 30 grams per minute. I don't know if I'm using the units that match what we did before, but you'll get the idea. How much liquid water leaves? Well, if everything in the problem statement stays the same, then it's going to be proportional. So I take my answers that I had, and so when it was 0.5, it was 0.5 grams per minute when it was 23.2. So I take my old answer, okay, and I multiply it times a ratio where I take the old basis and the new basis, and this gives me a way to mathematically come up with a new answer of how much water will leave. And so in this particular case, I can use this as a scaling factor, and I just take, so the answer I want, so start with the old answer, divide by the old basis, multiply by the new basis, and that will get me the new answer. And I can use this on any of my flow rates, whether it's mass or mole fractions. And it's a very easy way, so I can work a problem one time and then vary it to meet different needs.